Hello everybody. In this video we're going to be going over section 10.1 Intermolecular Forces. The first thing I want to do is make a clear distinction for you guys between these two terms that sound very similar, so they can be a little confusing. There are intramolecular forces and there are intermolecular forces. So intra means from within, and these are forces or interactions that occur within a molecule. So these include actually our chemical bonds that are going to give us like the rigid overall shape and connectivity of the molecule, and can also include some longer range interactions that are going to dictate what sort of conformations are going to be the most stable, even when we do have some freedom of movement around something like this single bond here that's able to rotate. The next is intermolecular forces. This is what we're actually interested in studying today. And these are interactions that occur between two or more molecules. So they're going to happen in between different molecules. And what they're going to do is they're going to dictate how these molecules wind up arranging to one another and what kind of strength these forces have are basically going to decide how sticky these molecules are, how much they want to stick to one another. Intermolecular forces have a strong effect on what we call bulk properties. So these are properties that we're able to observe in our macroscopic domain. If we look at the increase of intermolecular forces from low to high, what's going to wind up happening is they're going to start to resist phase changes. Okay, so the more intermolecular forces we have, the less something's going to say want to boil and release those atoms or molecules out into the atmosphere, the more they're going to resist melting and moving away from each other out of a crystalline shape and being able to slide around next to each other. And then conversely here, volatility is going to go down because volatility requires that a molecule be released out into the atmosphere. It's kind of hard to see here, so what I'd like to do is take a look at this little simulation for you guys. So we're going to go to phase changes here, and we're going to take a look. We're going to go to adjustable attraction, okay, and we're going to take a look at this. So if we take a look at this guy here, we now have a little shape here, and we can see that it's not moving to fill the size of its container. It's not even changing shape to fit the bottom of the container here. So this is what we would call a solid. We're simulating a solid right now. Let's see what happens. And we can see up here that we have strong interaction strength. Let's see what happens if we decrease that. So once we decrease it a little, we start to see them move a little bit further away from each other. Okay, they're moving a little bit more freely than they were before. If we turn it all the way down, we'll start to see them actually be able to move past one another. And as this continues on, they're going to be able to have some freedom of movement at the edges, and eventually it starts to take the shape of the bottom of the container. So we're now simulating a liquid. So decreasing the interaction strength caused our material, when we had the exact same temperature, to be a liquid instead of a solid. If we increase the temperature a little bit, we can start to see it approximate something that looks like boiling. We've got more and more of these atoms moving up to fill the volume of the container. And now we have something that looks a lot like a gas, where we have everything free moving and it's going and filling the container, striking the walls of the container at all sides. And we can see that our pressure has now increased. Let's see what happens if we increase the interaction strength and see if we can see what that stickiness I was talking about before. So now we see that these gas molecules are sticking to each other. They're starting to coalesce into little groups. They're starting to fill back into the bottom of the container. And if we cool it just a little bit, we can start to see condensation. And it'll go back to filling the bottom of the container and being a liquid. So when I have weak interactions, I have something approximating a gas. When I have strong interactions, I get something approximating a liquid. All right, now that we have an idea why we care about intermolecular forces, let's talk about the different types of intermolecular forces. We have three big intermolecular forces that we're interested in studying. We have dispersion forces, sometimes called London dispersion forces. You may see van der Waal forces in some texts, okay? We have dipole-dipole interactions, and we have hydrogen bonding. As we move down this list, they have increasing amount of strength. Each of them is caused by a different phenomenon, and we're going to talk about what these different phenomena are right now, starting with dispersion forces. So, as is often the case, we want to kind of start thinking about these things by considering a very simple system and thinking about it in kind of a statistical nature. So, you may remember from Gen Chem 1 that this is basically our model for the helium atom. We have a nucleus in the center that's positively charged. We have two electrons. Those two electrons are moving around in this sphere here that is a 1s orbital. And most of the time, these electrons are going to be pretty evenly distributed across this 1s orbital. But every once in a while, what's going to happen is these electrons are going to gather together in one side of the orbital. What that's going to cause is an area of increased electron density. And that's going to lead to a partial negative charge. And we indicate that with this lowercase Greek letter delta and a little negative symbol here. Over here, we have an area of decreased electron density, and it's going to have a partial positive charge. Okay? This separation of charge that we have here is our dipole. Okay? Di means two. Poles mean that they have opposite polarities. And while normally this is just going to be a one-time thing, it's going to have this instantaneous dipole and then it's going to go back to being normal like one of these guys. If I add enough pressure and decrease the temperature enough, I can bring these helium atoms close to one another. And what's going to happen in that case is an instantaneous dipole is going to happen in one of them. It's going to create that charge separation, and it's going to induce a instantaneous dipole in its neighbor. So all the electrons in this guy are going to be attracted to this partial positive charge. That's going to lead to a partial positive charge here. This guy's electrons are going to rush over there, and it's just going to keep propagating throughout the bulk of the material. Couple of key takeaways here. These instantaneous dipoles can be induced in any molecular atom. So all of our molecules or atoms are going to have dispersion forces. This is a weak and non-permanent interaction. So it's not going to take much energy for me to break this up. Okay? Something like liquid helium boils at a very low temperature. So if you just have purely dispersive interactions, they're not going to be very strong. The interaction becomes stronger with increased formula mass, atomic mass, and effective surface area. So if I have a large molecule or a large atom, they're going to have greater dispersive attraction to one another. And the increase in effective surface area basically means that if I have molecules that are more spread out, then they have more surface area available to them to have dispersive interactions. So, for instance, let's take a look at some organic molecules here, what we call nonpolar organic molecules. So, organic molecules that only experience dispersive intermolecular interactions, okay, they're often just have carbon and hydrogen. All right. The larger of these molecules are going to have stronger interactions. And the branching is going to decrease the dispersive interactions. So here we have an example where we have the exact same molecule in the sense that it is what we call a constitutional isomer. Okay, it has the same number of carbon and hydrogen atoms, but they're connected differently. This one that has a high degree of what we call branching looks very much like a sphere, and we know from geometry that a sphere is going to have the maximum amount of internal volume and the minimal amount of surface area. As we start to decrease the amount of branching, we draw this molecule out, exposing more and more of that internal volume to the outside, which can then have dispersive interactions with other molecules. We can see that trend experimentally if I've drawn out here in this stick figure type fashion those exact same molecules, and we can see that as we decrease the amount of branching that's happening, we get a clear increase in the boiling point for those molecules. Okay, let's talk now about dipole interactions. The first thing I want to do is give you guys like a little bit of a review here. We learned in Gen Chem 1 that there is a property called electronegativity. Electronegativity is the tendency for an atom to draw electrons towards itself. We also learned that the lowest electronegativity is going to be seen in the bottom left of the periodic table. And we're going to see an increasing trend as we move diagonally across, with the highest electron negativity seen in the elements in the top right of the periodic table. You can always refer back to this table if you need to. It's in our textbook if you want to know what the electronegativity of a specific type of atom is. All right, here's where we have to be really clear about our language again. We have bond dipoles, and these are intramolecular interactions. So these occur within a molecule, all right, and they lead to dipole moments, which are the intermolecular interactions we're actually interested in studying. They arise when two atoms with different electronegativity are bound to one another. So in our simplest example, where we just have two atoms here with our hydrofluoric acid here, what's going to happen is we have less electronegative hydrogen, and we have more electronegative fluorine. Electrons are going to be drawn now not just across an atom, but across a bond, okay? And we're going to see a partial positive charge on this side of the molecule and a partial negative charge on this side of the molecule. The fact that we have drawn this charge differential over a longer distance is what makes this interaction stronger than just purely dispersive forces. We've also introduced a new way of talking about it with this guy right here. This is a vector, and a vector is a mathematical object, and it has two different properties to it. It has a direction where it's going to start at the less electronegative atom and point towards the more electronegative atom, and it has a magnitude which is basically the strength of this interaction, and is going to be indicated by the length of that vector. Okay, the greater the difference in electronegativity between these two atoms, the larger this vector is going to be. Every time we have a bond where we have a difference in electronegativity across it, we're going to have a bond dipole associated with it. So in the case of water here, we have two bond dipoles that are both pointing towards oxygen, and they're going to lead to different areas around the molecule of low electron density with partial charges and areas of higher electron density with negative charges. So dipole moments are found by summing a molecule's bond dipole vectors. Okay, there is a mathematical way of summing these, but we can actually do it graphically pretty easy. So all we have to do is take one of our bond dipoles. I'm going to start with this one here, and I'm going to put the tail such that it starts at my central atom there. And then I'm going to move the other one so that its tail goes to the head of the first one, right there. So you can just imagine I just moved this guy here, and then I moved this guy here so that his tail is right at the head of the first one, and then his head's right there. Then I'm going to draw an arrow starting from the tail of the first one, pointing towards the head of the last one, and that's what becomes my overall dipole moment for the molecule. And this is going to lead to the type of intermolecular interactions that we're interested in. In our simpler case down here where we just have one bond dipole, it's pretty easy. All we do is just move it down so that the tail of this guy is on our more electronegative atom, and that just becomes the bond or the dipole moment for the molecule. So there's a few ways that this can play out. We can have additive vectors, so when they're both pointing in the same direction, like in our case of our hydrogen cyanide here, they will go head to tail, and we will wind up with an overall dipole moment that is larger than either of our bond dipoles. And they can be subtractive. Okay, and this can play out in a few different ways too. So in this case where we have CO2, we have opposing bond dipoles of the same magnitude. They're going to cancel each other out. So even though there is polarity here, there are bond dipoles in CO2, a difference in electronegativity, the overall molecule itself has no bond dipole and does not participate in dipole-dipole interactions. In a case like this where they oppose but they have different magnitudes, we just wind up with a weaker, smaller overall dipole moment for the molecule. And here we have a special case where I'm going to do a little foreshadowing for organic chemistry again. We have the case of carbon being the more electronegative atom. It's in this tetrahedral formation with hydrogen at each one of the ends of the bonds. And it's got bond dipoles that are pointing towards those carbons. Now, because this is a three-dimensional shape, it's pretty difficult to imagine how all the math is going to work out when we add all those vectors together. But if we did, what we would see is that overall we get no dipole moment, which is why molecules that just have carbon and hydrogen tend to be nonpolar. So, when two molecules with dipoles come close to one another, their dipoles align, leading to an interaction. Okay, so here I have an example of formaldehyde where it has a dipole, okay, and it's going to interact in such a way that that dipole is going to line up. Remember that that's where the negative end is, because it's our more electronegative atom, with the more positive end of the dipole on the other atom, and they're going to align to one another, creating an interaction that's going to start to bring them closer together and cause them to resist phase changes. We can see that experimentally here. We have an example here of formaldehyde and ethane. So these guys have roughly the exact same formula mass, and we learned that with dispersive forces, those are going to get stronger with greater formula mass, so they should have roughly equal dispersive forces. Yet the boiling point of formaldehyde is a full 70 degrees higher than the boiling point for ethane, and that's because of those dipole-dipole interactions. Hydrogen bonding. So hydrogen bonding is a special case of dipole-dipole interactions. It occurs when hydrogen is bound to a sufficiently electronegative atom. And when I say that, I mean oxygen, nitrogen, or fluorine. The single electron on the atom is drawn far away from the nucleus. And what this results in is a highly concentrated partial charge, leading to a stronger than normal interaction. So while this is a strong interaction that can have a pretty large effect on the bulk properties, it is poorly named. Hydrogen bonding is not an actual chemical bond, but a different type of intermolecular interaction. So we have a good example here when we analyze the hydrides from group 17, 16, and 15. So basically, we're just going down the periodic table in 3 columns, okay? And what we would expect to be the normal trend seems to hold here. As we're getting larger and larger, moving down that periodic table, higher and higher formula masses, we're seeing higher and higher boiling points. Yet all of a sudden, when we get to the lightest ones with water, HF, or ammonia here, we see a really large increase in the boiling point, even with even larger than the heaviest of these atoms. And that is due to the strong effect of the hydrogen bonding that's occurring and holding those water molecules or HF molecules together. Hydrogen bonding plays an important role in biochemistry. In particular, it helps to guide what are these really large molecules that make up living things into the conformations that they need to hold on that larger scale. A great example of that is in DNA, where we have our DNA base pairs. These are basically our rungs on the DNA ladder, if you guys have seen an image of that before. And those rungs are being held together by hydrogen bonding between the DNA base pairs. So here are conclusions. All molecules and atoms are subject to dispersive forces that induce partial charge differentials, leading to instantaneous dipoles. Differences in the electronegativity of atoms bound together lead to bond dipoles. Bond dipoles can sum to produce dipole moments depending on molecular geometry. Hydrogen bound to oxygen, nitrogen, or fluorine results in hydrogen bonding, a special type of dipole-dipole interaction that's very strong. And intermolecular forces have a significant impact on the bulk properties of a substance.